Hi everyone, and welcome back to Physics 11. So in this video we're going to be looking at the law of conservation of energy. So now that we know about work, potential energy, kinetic energy, and how the change in energy, whether it's potential or kinetic, can create work, let's combine it all together and see what kind of problems we can solve. So the law of conservation of energy is, again, the same law that you learned in your grade 9 science, and then when you learned about potential kinetic energy in grade 10, same thing. And this is also known as the first law of thermodynamics, which again is one of the oldest laws in physics that hasn't been altered in a long time. So energy cannot be created or destroyed, can only be changed from one form into another. So that's basically the gist of this first law. So if you have a closed system means that you have finite amount of energy in it, then all you're going to do is just change it from one form to another. You won't be able to lose or gain any energy. So for most problems that we're going to be doing, we're going to be dealing with closed systems, which means we're not going to have losses due to heat or friction or air resistance or anything like that. Or basically we're going to ignore them or assume they're negligible. But in real life, of course, you do have open systems for the most part. For example, planet Earth is an open system because we constantly get energy from the sun. But in Physics 11, most problems are going to be closed systems. So just keep that in mind. So imagine this. Let's say you have a baseball that's been thrown into the air. We know that potential energy depends on the position. So let's say if we start at the bottom here, this is going to be our reference point. This is going to be our zero, right? So from this point onwards, the higher you go, the more potential energy you'll have. So at the top here, right here, we're going to have maximum potential energy. And you start when you throw the ball, you're going to input kinetic energy into it to make it go up. But as it gets to the highest point, the maximum height here, basically it stops. So it's no longer moving for an instant. So after that instant, it's going to start falling back down. And it's basically stopped here. So it's going to speed up more and more. If you remember your kinematics unit, it's going to increase its speed and it's going to go fastest again at the bottom. So when it comes back to the 0 point, it's going to go fastest again. So at the bottom here, at the start and at the end, we're going to have maximum kinetic energy and minimum potential energy, or could be zero potential energy depending where your reference point is. Okay? So again, as the ball travels upwards, the kinetic energy is converted into potential energy. Again, we're neglecting any air resistance or friction that we have here. And as the ball falls downwards, the potential energy is converted into kinetic energy. So again, we're treating this as a closed system. So the total amount of energy that we have here remains constant. So again, any changes in kinetic and potential, basically it's just conversions. We're not losing or gaining any energy. Now, a very common problem in physics is going to be pendulum. So pendulum can be, for example, like an old pocket watch on a string or a chain, or maybe like the grandfather's clock that basically has a pendulum, which is a weight on a fixed rigid stem, and it swings back and forth, left to right. In this case, as it swings, the mass, this mass right here, is going to be at highest height compared to, again, our reference point, which is going to be down here. So this height here, right, delta H, is going to go from the highest to the lowest. So here we're going to have maximum potential energy, and as it swings down, it's going to speed up. It's going to have maximum kinetic energy. So after this, it's going to keep going up, and again, it's going to get to maximum height, and again, we're going to have maximum kinetic energy. In this case, we're talking about potential energy. And no kinetic energy left. A roller coaster works on the same principle. It takes the potential energy at the beginning, and then it's going to convert into kinetic energy as it starts to go down from the highest hill. Now, one of the questions is, for example, how come the largest hill is always at the beginning? Well, the reason is because a roller coaster is not a closed system. In reality, it's an open system, so there's going to be losses of energy. So in this case, as the car goes down, it's going to lose energy to heat, friction, sound, light perhaps, even if you see sparks going off the wheels there. So in this case, the roller coaster is not a closed system, it's an open system. So it will lose some energy. So to account for the losses of energy, they have to compensate with the highest hill first, so then they have enough energy in the second hill or the third hill. Otherwise, you're just gonna stop at some point and just roll back. So you're not gonna go over the hill because you're not gonna have enough, because in this case, this is an open system. So you are losing some energy on every hill. So let's take a look at a summary. So when you have conservative forces, and conservative forces are forces that only depend on position, so for example, like gravity and spring force, work on an object, the kinetic energy is converted into potential energy and vice versa. So again, conservative forces like gravity, like mg, and your your spring force, like your kx, right? So whenever you have those type of forces, then you have your conversion without any loss. Now, when there's an external force, for example, like friction, you are going to lose some energy, okay? And that's inevitable. For example, any engine, electric or internal combustion or steam engine, doesn't matter what it is, they all have a theoretical maximum efficiency. And we're actually going to talk about efficiency later on. But the point I was trying to make here is that in most cases, all the systems in real life are open system, and you will always lose some of the energy, okay? So for example, internal combustion engine has an efficiency, theoretical maximum efficiency around 60%, which means that 40% of energy is always lost. No matter how well you make your engine, there's always going to be loss of energy because of friction. So again, external forces like friction, you're always going to lose some energy. So energy is not conserved. So friction converts some energy into heat for the most part, sound, and light. So those are the common ways you can lose energy. So for example, here's a real life scenario. We have a time lapse of this tennis ball that's bouncing. You can see that it starts high, and then on the next bounce, it's much lower. And then on the third bounce, it's lower still, and so on. And at some point, it's going to just stay on the ground, not bounce anymore, because with every bounce, the ball compresses, loses some energy, and then doesn't have enough energy to go back up to the same height as before. So because of that, every consecutive bounce is lower and lower. So again, in real life, we don't have closed systems. There's not a lot of closed systems. So you're always going to have some loss of energy. But for a lot of the problems, we can assume or pretend like the energy is conserved, and we can approximate our solutions. So a lot of the questions we're going to do are going to be approximations, not actual answers in real life, because we know that in real life we have open systems, so there are always going to be some energy loss. But nevertheless, we can approximate a lot of the problems actually to fairly high degree of accuracy. And then later on, you can definitely include energy losses. You can include your heat energy as well, to have even better answers. And we might have, if we have time, we might look at some cases with friction included. So the law of conservation of energy, again, your first law of thermodynamics, states that the change in kinetic energy equals to the negative change in potential energy. So this means that if you have positive kinetic energy, change in kinetic energy means that you're going to have a loss in potential energy. Or let's say if you move this negative to the other side, that means that any gain in potential energy is going to equal to a loss in kinetic energy. And if you move them to one side, both of these move to one side, the sum of changes in energy should equal to 0. So in a closed system, there's no energy loss. So the total initial energy must equal to the total final energy. Again, this is only applicable to closed systems where you have unchanged amount of energy. So in that case, we're going to have the following. We're going to have initial kinetic energy plus the initial potential energy is going to equal to the final kinetic energy plus the final potential energy. Okay? Which means that if you substitute each of these with the actual equation for kinetic energy, potential energy, you're going to end up with 1/2 mv squared initial plus mgh initial equal to 1/2 mv squared final plus mgh final. And this equation right here, you can use to solve a lot of different problems. And if you want to have better explanation or more steps to get to this point, I suggest you read the textbook. So for example, if I jump to it quickly, this is section 7.4, conservative forces and potential energy. And again, it goes through the explanation of what I just summarized on that slide. So how do you go from kinetic energy to the change in potential equal to the change in kinetic. Again, only applicable to conservative forces and closed system. So again, make sure you read the section 7.4 in your textbook on this. So let's see how we can use this to solve some of the problems. Let's say we have a skateboarder. So while jumping over the Great Wall of China, 82 kilogram skateboarder, it needs to leave the ramp traveling at 78 kilometers an hour. So the first step is always to convert your units. So in this case, the quick way of converting is to divide it by 3.6, and you're gonna get your meters per second. So this is gonna be 21.67 meters per second. So the question is, how much potential energy does he need to start with? So in order to clear the Great Wall of China. So in this case, let's start with the equation. Our kinetic energy, our initial kinetic energy, let me use I for initial so it's not confused with zeros here. So you can use your EK naught or EKI if you want, it's up to you, plus the initial potential energy is going to equal to the final kinetic energy plus the final potential energy. Okay. Now in this case, we know that the skateboard is not going to jump up on the skateboard. It's going to roll down first. So he's not going to have any kinetic energy. So he's going to start from rest. So this thing is going to be 0 because he starts from rest, right? So if you have a ramp that you want to jump over, right? Let's say this is the wall here. He has to be somewhere here. This would be his starting position. So he's going to start rest at the highest point. He's going to roll down, leave the ramp, and then hopefully clear the wall. So we know the kinetic energy at the beginning is going to be 0. So all he has is potential energy at first, which means that at the end, after the jump, he's not going to have any potential energy at the bottom. So once he lands, let's say at the bottom here, the potential energy is going to be 0. After landing. Okay, so he's going to land, and again, he's going to come to the bottom here, and that's going to be his final position, right? So this is going to be his 0 potential energy. So this is a ground, basically. So then we're only left with the initial potential energy equal to final kinetic energy. So now we simplified our equation quite a bit. So because we're looking for the potential energy, right, we're going to leave the left side alone. We're going to write our potential energy equal to the EKF, and we know that kinetic energy is 1/2 mv squared, and this is our final velocity. We can then plug in the values. We know that the final velocity when he leaves the ramp is going to be 78 kilometers an hour, or 21.67 meters per second. By the way, this is 2 sig figs here. So even though you want to use this whole number here, you have to keep in mind that this should be only 2 sig figs. So all we have to do is plug in the mass, which is 82, plug in the speed, which is 21.67, and then don't forget the squared, and then divide by 2. So this is 2 sig figs, this is 2 sig figs. So remember, 2 sig figs here only. So you would only use 2 sig figs in your calculation. So whatever you get is going to be rounded to 2 sig figs. So when you do the calculation, you're going to get 19,247 joules. But again, because we had to round to just 2 sig figs, we're going to round this to basically 19,000. So that's the initial potential energy that the skater needs in order to leave with enough speed to clear the wall. So in this case, now we want to get into the actual definition of potential energy, which is mgh. So we're going to take the same equation as before and just going to take our potential energy and say that, okay, this is going to equal to mgh initial, right? And this is what we actually care about. We care about the hi here. Since we already found what this is going to equal, this is going to equal to 19,247 joules. We know what this value is. We know the mass of the skater. We know the g value. Basically one unknown only the initial height. So all we have to do is rearrange this for initial height, and that's it. So hi is going to equal to the potential energy, initial potential energy, divided by mg. So in this case, again, we're going to use this number here. So this is what you want to use in your calculations. So use to calculate. Okay, but keep in mind that it's only 2 sig figs. So you're going to use 19,247 over 82 times 9.8. So again, 2 sig figs over 2 sig figs. So you should get 2 sig figs in your final answer, which happens to be 24 meters. So the minimum height of the ramp should be 24 meters. All right, so in this case, this height corresponds to, what are you talking about? Initial, so to be on this side, sorry. So it'd be the starting position, this should be 24 meters. Okay? All right, I don't know what's going on there. So that initial height for the ramp should be 24 meters for him to have 78 kilometers an hour as it leaves the ramp. So 24 meters, that's, I don't know, this is like 5 stories. So it's pretty high up. All right, so let's take a look at another example. In this case, we have a trampoline. Dunk artist is bouncing to maximum height of 4.8 meters before launching himself towards the hoop. At the top of his arc, he is 3.2 meters above the ground. How fast is he traveling at this point? All right, so in our case, we're looking for the speed. So we're looking at the kinetic energy. We're trying to find the kinetic energy. So let's see what we can do. Let's start with the equation. So we have our initial kinetic energy plus initial potential energy equal to the final kinetic plus the final potential. Okay, now let's see what we can get rid of here. Now in this case, let's see, he bounces to maximum height of 4.8 meters before launching himself towards the hoop. So that means that at the maximum height of 4.8 meters, he does not have any kinetic energy. So that means that initial kinetic energy we can ignore here, and we're only going to consider the initial potential energy, which is going to be based on the initial vertical height of 4.8 meters. So we managed to get rid of the kinetic energy because he's high up, 4.8 meters. He's going to bounce on trampoline, then he's going to fly towards the hoop. So in this case, we're going to be left with mg initial height equal to the kinetic energy. So it's going to be mv final squared over 2 plus the mgh final. Now, why do we have kinetic and potential energy on the other side? Well, he has to be moving, right? And he has to bounce to the height of the hoop. So it's going to be less than 4.8 meters, of course. So he's going to have a mix of energies after he bounces and flies towards the hoop. So he's going to be moving and he's going to be at some height. He's not going to be on the ground, of course. So he will have both energies as he dunks the ball. Now, if you notice, in each of the steps here, in each of the terms, rather, we have the mass. And because the mass is going to be the same, the mass is not going to change. Notice that it's not even given in the question. Because the mass is going to be constant, we actually get rid of it. We can factor it out from each of the terms, and then they end up canceling away. So what I mean by this, if you're not sure how that happens, let me show you the steps. So we have factor out the m. So you're left with just the v squared over 2 here, plus the g times final height. And notice here that if you divide both sides by m, it just goes away. So this goes away with that. So that's why we can just, if you have the same term, the same variable in each term, you can just cross it out because it will end up reducing away. So then we're left with this simplified version of this equation. And because we care about how fast he's traveling, so we care about the final velocity, we basically now had to solve this for our v final, which means we need to move our g times our h final to the left. So let's do that. All right, so we're left with just this. Now we need to move the 2, so multiply both the left side by 2 and then take the square root. So let's do that. So multiply by 2 means we're going to move the 2 to the front. So g times the height. Okay, and the final step, of course, is to take the square root. So let's do that on this side. Let me write the final velocity on the left side now and take the square root of all of this. All right, so let's close that, and we get our equation for velocity, for final velocity. So now we can plug in the numbers. And again, g remains constant here, so I guess I need another set of parentheses here. So our initial height was 4.8 meters. Our final height is going to be 3.2 meters, which is the height of the basketball hoop. And again, we have the 9.8 here. You could have factored out the g if you wanted to. Okay, so punch this into the calculator. We see we're going to have, we should end up with just a fix. So 5.6 meters per second is what I got here for the final velocity. Okay. So again, this is our h final, hi. So there you go. Now you can solve quite complex problems fairly quickly by knowing the concept of conservation of energy. So let's take a look at one last problem here. So in this case, again, we have a 65 kilogram snowboarder, starts at rest, travels down a hill into a gully and back up to the other side as shown. Find his speed at the top of the second hill. So this was his starting point right here, right? So we have 45 meters to start. So his initial height is 45. His final height is 25 meters. So the difference between these two is going to be the change in potential energy. So this is going to be your delta P. So between here and there. All right, now as he leaves the top of the first hill, he's going to come down to the bottom. So this is going to be the maximum potential, kinetic energy. So at this point we have maximum at the first hill. This is the max potential energy right here. And this is going to be the maximum kinetic energy. Down here, he's going to have, on the second hill, it's going to have a mix of potential energy and kinetic energy. Again, we're assuming that this is a closed system with no loss of energy to friction or air resistance. So all the energy that he starts with is going to be transformed into a mix of energies, in this case, potential and kinetic. So again, the question is, find his speed at the top of the second hill. So we know he's going to have his kinetic energy, and once you know your final kinetic energy, then you can find his final speed, or not necessarily final, but the speed at this at the hill of the second hill. So now there's different ways you can approach this problem. You can say that your reference point is going to be the bottom. You can set your 0 to be at the bottom here, or perhaps the easier way is to set this point right here, which is basically the height of the second hill, as your 0. Again, it's up to you how you want to solve this, and this just happens to be a little quicker because at this point we are able to remove some of the energies. For example, if you say that this is your 0, that means that at this point you have 0 kinetic, only potential energy, and at this point you're going to have 0 potential energy and all kinetic energy. Okay? Whereas if you make this your 0, you're going to have a mix of energies. Here you only have potential energy, 0 kinetic, but at this point you can have both potential and kinetic energy. In this case, because you're given the height, you probably can solve it either way. But if you make this your reference point, you can actually get rid of 2 terms in your equation. So let me show you what I mean. So here's our equation: our initial potential energy plus the initial kinetic energy equal to the final potential plus final kinetic energy. So if I make my reference point right here, this means that again I have 0 kinetic initial, which means this will go away, only initial potential energy. And then at this point I have 0 potential energy because it's at the lowest point, so I can get rid of the final potential energy, which only leaves me with the final kinetic energy. So this simplifies our equation quite a bit. If you make this your reference, you can't get rid of this final potential energy. You have to include it, which in this case you can because you had the value for the height, so you can still use it. But it's easier if you just get rid of it, so it saves us a step. So let's make our 0 here, and again this will go away, so this will go to 0 because again of its position. So you only left with the potential energy, or initial potential energy, equal to the final kinetic energy. And because we're interested in the speed, we're interested in the velocity. So mv squared over 2. Now, we'll need to calculate the initial potential energy, which is going to be the difference between 45 and 25. And then, of course, solve this for the velocity. Now, in this case, let's plug in, actually, let's do this. Potential energy is going to be mgh, so mgh initial equal to mv final squared over 2. The masses are going to be the same, so we can reduce those away. Okay, and now we're left with the basically hi. Now our hi here is going to be 45 minus 25, right? So that's going to be our initial height. So that's one extra step you have to do on the side, I guess. So in this case, this is not going to be our hi then anymore. We're going to make our hi the difference between these two. So our hi is going to be this height right there. Or let me just write it here. Our hi is going to be 45 minus 25, which is, of course, 20 meters. So that's going to be the value you're going to plug in for your initial height. So let's rearrange this for the final velocity. which means we're going to multiply both sides by 2. So we're going to get 2ghi equal to v final squared. Okay, then take the square root. So our v final is going to equal the square root of 2ghi. And then plug in the numbers. So 2 times 9.8 times the initial height, which is going to be 20. And again, this case 20, least number of decimals, so this should be 2 suffix. So I should include a decimal point right there. So decimal point there, which means that in my calculation, I should end up with 2 suffix in the final answer. So when you do the multiplication and take the square root, you end up with 20.0 meters per second. So that's going to be the final speed at this second hill. Okay, so again, there's more than one way you could have solved this problem. Like I said, you could have made your reference at the very bottom, but that just means you're going to have an extra term, which is fine. You can still do it that way. But in this case, because I made my reference here, I managed to get rid of 2 terms, which simplified my expression quite a bit. So again, in this case, you can find the speed at second hill. For example, if you were, wanted to know what the speed at this point, right? You can do similar steps, but in this case, you have to make your reference down here. So the problems can be, varying. As long as you know the final height, you can find the velocity, no matter where along this track you're asked to find the velocity. So that's kind of the benefit of energy system, or rather approach, conservation of energy approach, because it allows you to solve quite complex systems without even knowing the mass of the object, as you can see. So it's a pretty useful way to solving a lot of the problems that would be quite difficult to do with just dynamics, because with dynamics you have to deal with vectors and actually becomes quite complicated. But with energy approach, it can be quite simple. All right, so you have some practice questions. Unfortunately, I have the answer key for it, so make sure you work through the problems, and if you have any questions, post them in the comments as a reply on Teams.